this section and the next section. So it's not difficult, there's just a lot to remember. So we're going to start out with the definition, some properties, how to calculate the dot product, and then we'll look at some applications. So we're going to start right off with the definition. Let's consider that we have some vector A in 3 space with components A1, A2, A3. And then we have the vector B, also in 3 space with components B1, B2, B3. Then the dot product. Notation is going to look exactly like you think it would. It's going to be A dotted with B. So that's the notation. Here's the way to calculate it. You are going to multiply the likewise components. So we're going to multiply A1 and B1, A2 and B2, A3 and B3, and then you're going to add them all together. So that's the dot product. As you'll notice, this is going to give you a scalar. So it's going to give you a number. Dot product is also sometimes called the scalar or the inner product. So if you are asked to find the scalar or inner product, just know that's the same as the dot product. Most of the time, I'm going to use the term dot product. Another thing to know is you can do this in 2 space as well. It works the same way. So if you do it in 2 space, you just don't have that third piece. Okay, so let's do an example. We are going to take the vector I, add 2j, subtract 3k, and we are going to dot it with 2j, subtract k. So what I'm going to do first is I'm going to write it in bracket notation because I think it's a little bit easier to do the dot product. This is 1, 2, negative 3. When dotting it with 0, 2, negative 1. So like we said, you're going to multiply likewise components and then add them together. So I'm going to multiply 1 and 0. I'm going to multiply 2 and 2, and negative 3 and negative 1. So we end up with 4, add 3, so we had a dot product of 7. Make sense? Not too bad? Okay, here are some properties of the dot product that you should know. First property is if I take A and I dot it with itself, that's the same as taking the norm of A and squaring it. Now, please remember that one set of bars most of the time indicates the norm. A lot of times I'll write 2 sets of bars, so those both mean the same. Another thing for you to know is if you take A and you dot it with B, that's the same as taking B and dotting it with A. What property is that called? Commutative. Yeah. You guys are not very good with your properties. If I take A and I dot it with the sum of B and C, you can probably guess this. That's going to be the same as A dotted with B and then adding A dotted with C. Got 2 more properties. Fourth one, if I take some constant C and I multiply it by A, and then I dot it with B, that's the same as dotting A and B together and then multiplying by C. Also the same as taking C, multiplying by B, and then dotting with A. And then last one, if I take the 0 vector and I dot it with A, I'm going to get 0. I don't know why we need to define that, but for some reason we do. Any questions on properties? No, I told you on your exams a lot of times I'm going to ask you to write a proof. So we are going to prove one of these. We're going to prove the first one. Okay, for a proof, anytime you start a proof, you always need to define what you're looking at. So in this case, our property involves vector A, so we need to define vector A. So we are going to let vector A be the vector in 3 space with A1, A2, A3 as the components. Then I told you what I like you to do is I prefer to start on one side of the equation and work down until I get back to the other side. So we are going to take A and dot it with itself. This is going to get us A1 times A1, so A1 squared, plus A2 squared, plus A3 squared, which is the square root of A1 squared plus A2 squared plus A3 squared, that whole quantity squared. Reason I need that is now equal to the norm of A squared. So the norm of A being the square root. And how could I indicate that I have finished my proof? QED? Or, anybody remember the other way? Little black box. Or filled in box, I guess, doesn't have to be black. Good? I know what you're thinking. That really wasn't a very satisfying proof. So let's do another one. We are going to prove the third property. So this time we have three different vectors we need to define, vectors A, B, and C. So we are going to let vector A be the same vector that it was before, A1, A2, A3. I'm going to say likewise for B and C. I'm fine if you do that on a test. So then we are starting with A dotted with the sum of B and C. So first thing we need to do is we need to write this out in bracket notation. So this will be A1, A2, A3, dotted with the sum of B1, B2, B3, adding C1, C2, C3. Before we do the dot product, we're going to need to find the sum in the parentheses. So we have A1, A2, A3 dotted with B1 plus C1, B2 plus C2, B3 plus C3. Okay, now I'm ready to take the dot product. So I have A1 multiplied by B1 plus C1 plus A2 times B2 plus C2 plus A3 times B3 plus C3. Now we're going to distribute everything. So we get A1 B1 plus A1 C1 plus A2 B2. Add A2 C2, add A3 B3, add A3 C3. We are very close to what we need to prove. What step do we need next? Or what step do you suggest? Take out an A? Like factor an A out of everything? They're not the same A though. Remember what we need to get to is we need A dot B plus A dot C. That's our goal. Do we have A dot B? Yeah, this. So it is a good practice to bring those together. So we have A1 B1 plus A2 B2 plus A3 B3. And then the C's are together. And now we can say that this is the expression of A dot B add A dot C. So that wasn't too bad, right? It's just a bunch of algebra, moving stuff around. Okay. Here's one of the big importances of the dot product is this next theorem. If you take A and you dot it with B, that is the same as the norm of A multiplied by the norm of B multiplied by cosine of theta. Theta being the angle between A and B. Do you guys want to do the proof? Well, luckily for you, I don't want to do it. So it's on page 848 if you want to know. It involves the law of cosines. If we're not doing it in class, though, it means you don't need to know it. But if you're interested, look at page 848. This brings us to a corollary. Oftentimes, you're going to be asked to find the angle between vectors A and B. So we often rewrite this as cosine of theta is A dot B divided by norm of A times the norm of B. Next example. We are going to find the angle between vector u, which is I subtract 2j plus 2k, and v, which is negative 3i plus 6j add 2k. Okay, so I want you to do this real quick. Find the angle between those two vectors, please. When you have an answer, check with the person next to you. It's going to depend. Okay, did we get an answer? Yeah. Did we get an acute or an obtuse angle? Obtuse. Okay, good, I did as well. Here is my work. So I got 2.12 radians or 121.6 degrees. You guys agree? Okay, can we move on? Did we need to see this still? No. Great. Okay, next thing that we need to talk about is interpreting the sign of the dot product. So the first example we did, we ended up with a positive dot product. The second example, you ended up with a negative dot product, so it is possible to have a negative dot product. We're going to use that theorem, A dot B is equal to the norm of A times the norm of B multiplied by cosine of theta. Now, what is affecting the sign of the dot product? The angle, right? Norm and norm, those are always going to be positive. So theta, cosine of theta, that's what's determining whether our dot product is positive or negative. So we have three different cases. That dot product could be positive, could be negative, and maybe it could be 0. If the dot product is positive, that means that cosine of theta is positive. What does that tell us about A and B then? What? Right, the angle between A and B is acute. If our dot product is negative, that means cosine is negative. What does that tell us about A and B? Obtuse. The angle between them is obtuse. What about if the dot product is 0? Orthogonal. Are there any other cases if you have two vectors besides the vectors being orthogonal or the angle between them being acute or obtuse? Is there anything else that could be going on with two vectors? If I'm asking you, the answer is probably yes. So what is the case that's not covered here? Nope. Parallel. If our vectors are parallel. How can you tell if the vectors are parallel besides looking at them? How would you tell from the dot product? What is it going to be equal to? No. If the vectors are parallel, what's cosine of theta going to be? 1, right? So then your A dot B is going to be equal to the product of the norms. Does that make sense? Okay, so that would be the case where your vectors are parallel. Okay, so what this leads us to is direction angles and direction cosines. Okay, so definition, the direction angles, there's 3 of them. Direction angles, we denote alpha, beta, that symbol. Do you guys know what this one is? Yeah. Gamma. So alpha, beta, and gamma, those are what we call the direction angles. We are going to define them between 0 and pi. So alpha, beta, gamma are the angles that your vector A makes with the positive x, y, and z axes. Their cosines are called the direction cosines. So sometimes you'll be asked for the direction angle, sometimes you'll be asked for the direction cosine. So let's say that we wanted to find alpha. We would start with that theorem that we had before. So the cosine of alpha. So this is going to be the angle between our vector and then the x-axis. The vector is going to be A. What vector can we use to represent the x-axis? What's a vector that goes along the positive x-axis? I, 1, 0, 0. So we're going to take A and we're going to dot it with I. And then we have the norm of A times the norm of I. Now, I is a unit vector, so it's convenient to use. In this case, the norm of I is going to be 1. So what this really gives us is that the cosine of alpha, in the numerator, that I is 1, 0, 0. So all that's going to be left is A1, the first component. That is 1, so over the norm of A. Likewise, cosine of beta then is going to be A2 over the norm of A. Cosine of gamma is going to be A3 over the norm of A. Now, you need to be very careful what you are asked for. A lot of times you'll be asked just for the direction cosine. So what I want is that fraction. I don't actually want you to solve for alpha, beta, and gamma. Sometimes you will be asked, though, to solve for them. A few things that I want us to notice. First thing I want you to notice, if you square all of those cosines and you add them up, what are you going to get? So square all of those, add them up. What do you get? Nothing?
Must be the dot product of A.
With what?
To get the angle between them.
Oh, guys. Okay, let's square all those, add them up. You get A1 squared plus A2 squared plus A3 squared all over the norm of A squared. But what is that? One? Oh, right? Just one? Are you guys with me? Because you're kind of just staring at me. Now we're good? Yeah. Okay, good. Other thing I want you to notice is that another way to express vector A would be the norm of A multiplied by the vector cosine of alpha, comma cosine of beta, comma cosine of gamma. Or sometimes this is written as A divided by the norm of A is equal to cosine of alpha, cosine of beta, cosine of gamma. Okay, so why would I bother to show this to you? What that shows us is that the direction cosines form a unit vector in the direction of A. So if we look at each of the direction cosines, we put them together, we're going to get a unit vector in the direction of A. Okay, next example. You are going to find the direction cosines of angle A, which is 2, -4, 4. And then I want you to approximate the direction angles to the nearest degree. So you are going to do that on your own. Take 3 or 4 minutes and see if you can come up with the direction cosines and then the direction angles. Once you have your 3 direction cosines and your 3 direction angles, check with the person next to you, please. Are we ready to go over? Yeah? Is it okay if I just show you my work? Okay. This is what I got. 1/3, negative 2/3, 2/3. Those are all the direction cosines, and then the angles below. All good? Any questions? Can I move my work? Okay. Next thing up. So another example. I want us to find the angle between a diagonal of a cube and one of its edges. Before we do any calculations of any type, it's probably a good idea to draw a figure. I'm going to draw my cube in the first octant. So draw yourself a cube. Okay, so what we want is we want the angle between one of the diagonals So I'm going to call this D. And any one of the edges. So it could be this edge, could be this edge, could be that edge. Can you guys picture what I'm going for there? I know it's a little hard to see. Okay, this diagonal, I'm going to call that point A. Right, it's a cube. Okay. So one thing that we know is we can call that diagonal vector A, because it goes from the origin to point A. So what do we need to find here? If it's the angle between a diagonal and one of the edges, what is that? It's one of the direction angles. Yeah, it's asking us to find a direction angle. Direction angle is the angle between your vector and the positive x, y, or z axis. All of your answers are going to be the same here, so it doesn't matter which direction angle we find. So I'm going to find alpha. Cosine of alpha is going to be the first component, which in this case is a, divided by the norm. So we are going to have to find the norm of this vector. It's going to be the square root of a squared plus a squared plus a squared. So the square root of 3a squared. So a root 3. That's what will go here. So we get our cosine of alpha then to be 1 over root 3. Our alpha then, if you trust me, is 0.955 radians, or 54.7 degrees. Questions? Are we doing okay so far? Okay. We've gotten about 60% of the way through the notes, so we have two options right now. We can keep going, and then tomorrow we'll take notes for maybe 10 minutes, and you'll have the rest of the time to work on homework. Or we could stop now, and I can let you start your homework with what you know already. Would we rather continue with the notes and do a shortened notes tomorrow?
Yeah.
Okay, great, me too. Next thing we need to talk about is projections. Okay, so here's what we're looking at. Let's say we have 3 points. We have point P, which is heading towards Q, and then we have some point R up here. Let's call this vector B. What we are interested in is projecting B in a different direction. So let's call this whole vector vector A. We are interested in projecting B down onto A to form some new vector. So we have a few different things that are going on. This is the notation for projection. So this is saying we are taking the vector projection of B onto A. So it's kind of like B's shadow onto A. So that would be this orange one right here that I drew in. It's like B's shadow down onto A. This is the notation if I'm asking you for a scalar projection. Of B onto A. It's going to give you a scalar instead of a vector. This one is assigned magnitude of the vector projection. So there are a few different formulas for these. If you're looking for the scalar projection, we can start out with the magnitude of b times the cosine of theta. If we replace the cosine of theta with what we learned earlier today, that's a dot b over the magnitude of a times the magnitude of b. So what that gives us is that the scalar projection is going to be a dot b over the magnitude of a. Okay, so as I said before, this is a magnitude, right? It's a single value. It's the size of the projection. So if we want to look for the formula for the actual projection itself, it's going to be the magnitude, so what we already got over here, so the size of the projection times the direction. Now, our direction is going to be a. But remember, with direction, we want it to be a unit vector. This already indicates size. So we're going to multiply that by a over the magnitude of a. So again, this is the direction. This is the magnitude. So then our formula to find the actual vector projection is going to be a dot b over the magnitude of a squared times vector a. So nothing cancels, that's just normally the way that it's written. Okay, ready for an example? Yeah. We are going to find the scalar and vector projection of vector b, which is 1, 1, 2, onto a, which is negative 2, 3, 1. And this is one that I want you guys to do. For normal, when you're ready, you can check with someone next to you, please. here is what I got. This is your scalar projection, and this is your vector projection. Did you guys get the same thing? Okay. Any questions? How do we feel about the dot product? It's not bad, right?